Hi everyone. Today we're going to study degrees and zeros of polynomial. Let's begin with degree of the polynomial. If p of x is a polynomial in x, the highest power of x in p of x is called the degree of the polynomial p of x. Examples, we have here 4 polynomials. The first is 4x plus 2. This is a polynomial in x. The highest power is 1. Remember that the degree of the constant 2 is 0. So in here, the degree is 1. Second polynomial, 2y squared minus 3y plus 4. This is a polynomial in y. And the highest power is 2 among the terms. So the degree is 2. Third polynomial is 5x cubed minus 4x squared plus x minus 2. The highest power is 3. So the degree is 3. Fourth polynomial, 7u raised to 6 minus 3 halves times u raised to 4 plus 4u squared plus u minus 8. This is a polynomial in the variable u. The highest power is 6, so the degree is 6. For the polynomial, when degree is 1, there is a special name for this, and we call this linear polynomial. When degree is 2, we call this quadratic polynomial. When degree is 3, we call this cubic polynomial. Let's go now to zero of a polynomial. If p of x is a polynomial in x, and if k is any real number, then the value obtained by replacing x by k in p of x is called the value of p of x at x equals k, and is denoted by p of k. A real number k is said to be a zero of a polynomial p of x if p of k equals 0. Example 1. Find the corresponding value of p of x equals x squared minus 3x minus 4 at x equals negative 1, x equals 2, and x equals 4. Let's begin with the value of the function at x equals negative 1. In symbol, we write p of negative 1. The function p of x is given here. So, what we're going to do is, we substitute all x by negative 1. So, the x squared becomes the square of negative 1 minus the 3x becomes 3 times negative 1. Then negative 4. Simplifying the square of negative 1, we have positive 1. Negative 3 times negative 1 is positive 3. Then the negative 4. Simplifying this, we have now 0. This is the value of p of negative 1. Then we go to the next at x equals 2. In symbol, we write p of 2. Evaluating the p of 2, we're going to substitute all x by 2. The x squared now becomes 2 squared minus 3x becomes 3 times 2, then minus 4. We simplify 2 squared as 4 minus 3 times 2 is 6, then we attach the negative 4. Simplifying 4 minus 6 minus 4, we have now negative 6. Then we go to at x equals 4. In symbol, we write p of 4. We're going to substitute all x by 4. So the x squared becomes 4 squared minus 3x becomes 3 times 4, then the minus 4. 4 squared is 16 minus 3 times 4 is 12, minus 4. When we simplify, the answer is 0. These are the corresponding values of p of x when x equals -1, at x equals 2, and x equals 4 respectively. Since p of -1 equals p of 4 and both are equal to 0, then -1 and 4 are zeros of the polynomial. Example 2. Find the zero of the polynomial p of x equals 2x plus 3. Step 1. Let k be the zero of the polynomial. Then we evaluate p of k, which means the p of x here becomes p of k, and this is now the value, 2k plus 3. Step 2. We set p of k equals 0, and we solve for k. Our equation is p of k equals 2k plus 3. Now this becomes 0. We can disregard the p of k, then we will solve here for k. This positive 3 we transpose to the right. We have now 2k equals -3. Then isolating k, we divide the left side and the right side by the coefficient of k, which is 2. By doing that, the value of k equals -3 over 2. This is the final answer. Example 3. Find the zeros of the polynomial p of x equals x squared minus 3x minus 4. Step 1. Let k be the zero of the polynomial. Then we evaluate p of k. The p of x becomes k squared minus 3k minus 4. Then step 2. We set p of k equals 0, then we solve for k. We copy our equation in here, then this is equal to 0. We can disregard the p of k symbol, and from here, we're going to solve for k. We can solve this by factoring, and this becomes k minus 4 times the quantity k plus 1, then equals 0. We equate each factor to 0, which means the k minus 4 equals 0 and the k plus 1 equals 0. Then we solve for k for each of these equations. In the first equation, we transpose the -4 to the right, so the value of k equals 4. In the second equation, we transpose the positive 1 to the right, so k equals -1. These are the values, and we call them zeros of the polynomial. Hi everyone! Today we're going to study geometrical meaning of the zeros of a polynomial. The zero of a polynomial p of x is the point where the graph y equals p of x intersects the x-axis. In general, given a polynomial p of x of degree n, the graph of y equals p of x intersects the x-axis at most n points. Therefore, a polynomial p of x of degree n has at most n zeros. Example 1. Find the zero of the linear polynomial 2x plus 3 and draw the graph y equals 2x plus 3. The linear polynomial 2x plus 3 we're going to equate to 0, then solve for x. So we write 2x plus 3 here equals 0. Trying to solve for x, let us isolate the x here. The positive 3 we transpose to the right, it becomes negative 3. Then we divide this equation by 2. The value of x equals negative 3 over 2. This is the zero of this linear polynomial. Now, let us graph our line, y equals 2x plus 3. We know that the graph of y equals ax plus b is a straight line. To graph this line, we're going to put some values for x, and eventually we will get the value for the y. Suppose we assign x equals negative 2. The value of y will be negative 1. Suppose x is positive 2. The value of y is 7. We simply substitute the value of x respectively to our function or the graph, and then we will get the value of y. Let us plot the 2 points and connect these points. So, this is now the graph of this function, y equals 2x plus 3. We can see that it is a line. Observing the graph, we can see that the graph intersects the x-axis at the point negative 3 over 2, 0. Thus, the 0 of the polynomial 2x plus 3 is the x-coordinate of the point where the graph of y equals 2x plus 3 intersects the x-axis. Remarks: in general, for a linear polynomial ax plus b, a here is not equal to 0. The graph of y equals ax plus b is a straight line, which intersects the x-axis at exactly one point, namely the negative b over a, 0. Therefore, the linear polynomial ax plus b, and this a not equal to 0, has exactly 1, 0, namely the x-coordinate of the point where the graph of y equals ax plus b intersects the x-axis. Example 2. Find the zeros of the quadratic polynomial x squared minus 3x minus 4. Let us equate to 0 and solve for x. We write our polynomial down here, and then this is equal to 0. Next, let us solve for x. We can do this by factoring. The factors of x squared minus 3x minus 4 are x minus 4 times x plus 1, both equal to 0. We equate each factor to 0 and solve for x. The first factor, x minus 4, equals 0, and the second factor, x plus 1, equals 0. Then we can solve for x. We transpose the negative 4 to the right. The first value of x equals 4. In the second equation, the positive 1 we transpose to the right. The second value of x equals negative 1. These are the zeros of the polynomial. Let us show the graph of y equals x squared minus 3x minus 4. When doing this, we can show some values of x, and eventually we can see the value of y. Here are corresponding values. Let us now plot the corresponding points, and we connect them by a smooth curve. So the graph is here. Please observe that the graph touches the x-axis at the point 4, 0, it's here, and negative 1, 0. Thus, the zeros of the quadratic polynomial x squared minus 3x minus 4 are x-coordinates of the points where the graph of y equals x squared minus 3x minus 4 intersects the x-axis. We have these remarks. For any quadratic polynomial, ax squared plus bx plus c. The a here not equal to 0. The graph of the corresponding equation y equals ax squared plus bx plus c has one of the two shapes, either open upwards like this or open downwards like this, depending on whether a is more than 0 or a is less than 0. The a more than 0 means a is positive and the graph will look like this. The a less than 0 means a is negative and the graph will look like this. These curves are called parabolas. We have three cases for zeros of quadratic polynomial. Given a quadratic polynomial p of x, the graph y equals p of x intersects the x-axis at most 2 points. So we have the three cases. Case 1, when we have two zeros. Let's begin with this. For case 1 with two zeros, it means the parabola intersects the x-axis at 2 points. We have here two examples. This is our first example. This parabola opens downward. We can see that the graph intersects the x-axis at 2 points. Here is another example. The parabola opens upward. We can see that the graph intersects the x-axis at 2 points. Next, case 2, when we have 1, 0. This means parabola intersects the x-axis at 1 point. Then let us show some examples. We have here two examples. In our first example, the parabola opens downward. The maximum point of this parabola intersects the x-axis, so it is only at 1 point. In our second example, the lowest point of the graph intersects the x-axis. That is why it intersects at only 1 point. Now case 3, when we have no 0, it means the parabola does not intersect the x-axis. We have here two examples. In our first example, the parabola opens upward. This parabola is located above the x-axis, so it does not intersect the x-axis. The second example is a parabola that opens downward, but it is located below the x-axis. That is why it does not intersect the x-axis. Example 3. Find the zeros of the cubic polynomial x cubed minus 4x. Let us equate this polynomial to 0 and solve for x. So we have this x cubed minus 4x equals 0. Let us do factoring. First, we factor out the common factor, which is x. We have here x times x squared minus 4 equals 0. But this x squared minus 4 is still factorable into x minus 2 times x plus 2. From here we can see that we have three factors. Then we are going to equate each factor to 0 and solve for x. The first factor x equals 0. Second factor x minus 2 equals 0. Third factor x plus 2 equals 0. The first value of x is already 0. For the second value, we look at the second equation. We solve for x. This negative 2 we transpose to the right, so we have the value of x equals 2. In the third equation, x plus 2 equals 0. Solving for x, we transpose positive 2 to the right. So we have x equals negative 2. Here are the three values of x. These are the zeros of the cubic polynomial. Let us show the graph of y equals x cubed minus 4x. First, let us assign some values for x, then solve for y. Here are the corresponding coordinates. Let us plot these coordinates and connect them with a smooth curve. The graph will look like this. The graph intersects the x-axis at 3 points, namely when x equals 2, when x equals 0, when x equals negative 2. Thus, the zeros of the cubic polynomial x cubed minus 4x are x-coordinates of the points where the graph of y equals x cubed minus 4x intersects the x-axis. Example 4. Given the graph below, what are the zeros of the polynomial? We can see that the graph intersects the x-axis at the points 0, 0, the origin, and 1, 0. By definition, the zeros of polynomial p of x are the x-coordinates of the points where the graph y equals p of x intersects the x-axis. Thus, the zeros of the polynomial are 0 and 1. Hi everyone. Today we're going to study relationship between zeros and coefficients of a quadratic polynomial. We learned that zero of a linear polynomial ax plus b is the negative of b over a. We can see here that the constant b is in the numerator, while a, which is the coefficient of x, is in the denominator, and this is negative. We will now see relationship between zeros and coefficients of a quadratic polynomial. If alpha and beta are the zeros of the quadratic polynomial p of x equals ax squared plus bx plus c. A is not equal to 0. Then x minus alpha and x minus beta are the factors of p of x. Therefore, ax squared plus bx plus c equals k times the quantity x minus alpha times x minus beta. Here, the k is a constant. Let us multiply this x minus alpha by x minus beta, and it will be like this. K, the constant outside, we have x squared minus the quantity alpha plus beta times x plus alpha times beta. Now, this k outside, let us distribute to all the terms inside. We have now this k x squared minus k times the quantity alpha plus beta times x, then plus k alpha beta. Now let us compare coefficients of x squared, x, and constant terms on both sides. On the left side, the coefficient of x squared is a. On the right side, the coefficient of x squared is k. So we write a equals k. For the coefficient of x on the left is b. On the right side, the coefficient of x is negative k times the quantity alpha plus beta. So we write it here. For the constant, we have c on the left side. On the right side, we have this k times alpha times beta. So we write it here. When we take the ratio of this b over a, we will derive this relationship that alpha plus beta equals the negative of b over a. Further, if we take the ratio of this c over a, we will have this relation. The product of alpha and beta equals c over a. Example 1. Find the zeros of the quadratic polynomial 2x squared minus 8x plus 6 and verify the relationship between the zeros and the coefficients. Let us factorize the trinomial by splitting the middle term. Our middle term here is the negative 8x. So, we're going to split as a sum of two terms. There is another thing that we should consider, that the product must be 12x squared. This 12x squared comes when we multiply 2x squared by 6. So, the trinomial 2x squared minus 8x plus 6 is now equal to 2x squared. We split this negative 8x into negative 6x and negative 2x. When we multiply the two terms here, we will get this 12x squared. And then the constant plus 6. What we're going to do here, we're going to group the first two terms and the last two terms. In the first two terms, there's a common factor, and that is 2x. What remains is the x minus 3 in the first group. Then, in the second group, there is a common factor, and that is the negative 2. When we factor it out, what remains in the second group are x minus 3. In these groups, there is a common binomial, and the common is the x minus 3. We can factor it out. So we have 2x minus 2 times the x minus 3. In our first factor here, a number 2 is common again. We can factor it out into 2 times x minus 1. Then we copy this x minus 3. Let us equate each factor with variable to 0. So we have this x minus 1 equals 0, x minus 3 equals 0. When we solve for x, in the first equation, x is equal to 1. In the second equation, x equals 3. These are the zeros of our polynomial, or we say these are the alpha and beta respectively. Now let us verify the relationship between zeros and the coefficients. Take note that in our polynomial, the value of a is 2, the value of b is negative 8, the value of c is 6. Now let's begin with the first relationship. The sum alpha plus beta equals negative b over a. Let us substitute the corresponding values. So we have 1 plus 3 equals the negative of negative 8, that is b, over a, which is 2. 1 plus 3 is 4 equals, the right side is also 4. The first relation is verified. The second relation is alpha times beta equals c over a. The values will be 1 times 3 equals 6 over 2. On the left side, it is 3. On the right side is also 3. So, they are equal. It means the second relation is also verified. Example 2. Find the zeros of the quadratic polynomial x squared plus 7x plus 10 and verify the relationship between the zeros and the coefficients. We are going to equate our polynomial to 0 and solve for x. So we write x squared plus 7x plus 10 equals 0. Let us solve the polynomial by factoring. So we have x plus 5 times x plus 2 equals 0. Let's equate each factor to 0 and solve for x. The first factor, x plus 5 equals 0. The second factor, x plus 2 equals 0. When we solve for x, in here, x equals negative 5. In the second equation, x equals negative 2. These are the zeros of our polynomial. Now let us verify the relationship. In the first is the sum relation. Alpha plus beta equals negative b over a. Let us substitute the corresponding values. Negative 5 plus negative 2 equals the negative of b is 7 over a, which is 1. The left side is negative 7 equals the right side, which is negative 7. So the first relation is verified. Second relationship, alpha times beta equals c over a. When we substitute the values, we have negative 5 times negative 2 equals 10 over 1. The left side is positive 10, while the right side is also positive 10. They are equal. So the second relationship is verified. Example 3. Find the zeros of the quadratic polynomial x squared minus 3 and verify the relationship between the zeros and the coefficients. Take note that the a value here is 1, b equals 0. There is no x variable, and c equals the constant negative 3. Now let us equate the polynomial to 0 and solve for x. So we have x squared minus 3 equals 0. When we solve for x, we can transpose this negative 3 to the right. So we have x squared equals 3. And then we take square root of both sides so that we can cancel the power 2 here. So square root of x squared equals plus or minus the square root of 3. The left side will be simplified into x, and on the right side, we have the two values of x, the square root of 3 or negative square root of 3. These two values are the zeros of the polynomial. Now let us verify. Alpha plus beta equals negative b over a. When we substitute the values, we have square root of 3 plus the negative square root of 3 equals the negative of 0 over 1. The left side is 0 equals the right side is also 0. So the first relationship is verified. Next, alpha times beta equals c over a. We substitute the values. Square root of 3 times the negative square root of 3 equals the negative 3 over 1. We multiply the radicals on the left. We have negative square root of 9 equals the right side is simply negative 3. We simplify the left side as negative 3. That is now equal to the right side, which is negative 3. Therefore, the second relationship is verified. Example 4. Find a quadratic polynomial, the sum and product of whose zeros are negative 3 and 2 respectively. Let the quadratic polynomial be ax squared plus bx plus c, and its zeros be alpha and beta. Given we have the alpha plus beta, the sum equals negative 3. The product alpha times beta equals 2. Remember that the sum relation is equal to the negative of b over a, and the product relation is equal to c over a. Take note that the sum and product are given as integers, meaning we can assume that A equals 1. If that happens, in the first relation, we can get that value of B, which is positive 3, while in the second relationship, we can get the value of C, with A equals 1, C equals positive 2. Therefore, one quadratic polynomial that fits the given conditions is x squared plus 3x plus 2. Hi everyone. Today we're going to study relationship between zeros and coefficients of a cubic polynomial. If alpha, beta, gamma are the zeros of the cubic polynomial ax cubed plus bx squared plus cx plus d, take note that a here is the coefficient of x cubed, b is the coefficient of x squared, c is the coefficient of x. Then alpha plus beta plus gamma equals the negative of the fraction b over a. Next, alpha times beta plus beta times gamma plus gamma times alpha equals c over a. Next, alpha times beta times gamma equals the negative of the fraction d over a. Example 1. Verify that 3, -1, -1/3 are the zeros of the cubic polynomial p of x equals 3x cubed minus 5x squared minus 11x minus 3, and then verify the relationship between the zeros and the coefficients. When we observe the polynomial, take note that a equals 3, b equals -5, c equals -11, d equals -3. Now, to verify that 3, -1, -1/3 are the zeros of the cubic polynomial, we need to check that p of 3 equals p of -1 equals p of -1/3, all equal to 0. Let's begin with p of 3. We substitute this 3 to all the x of our polynomial. So we have this 3 times 3 cubed minus 5 times 3 squared minus 11 times 3, then minus 3. This 3 cubed times 3 will be 81 minus 3 squared is 9 times 5 becomes 45 minus 11 times 3 is 33. Then we have this -3. When we simplify this, the answer is 0. So p of 3 is 0. Let's proceed to p of -1. Evaluating this, we have now this 3 times the cube of -1 minus 5 times the square of -1 minus 11 times -1, then minus 3. Simplifying further, the cube of -1 is -1 times 3 is -3. Then the square of -1 is +1 times the -5. We have this -5 here. Then -1 times -11, we have +11. Then we attach the -3 constant. When we simplify this, we will get 0. Thus, the p of -1 is 0. Now we go to p of negative 1/3. We have now this 3 times the cube of negative 1/3 minus 5 times the square of negative 1/3 minus 11 times the negative 1/3 minus 3. When we simplify the cube of negative 1/3, we will get negative 1 over 27 times the 3 here, we will get the negative of 1 over 9. Then, the square of negative 1/3 is positive 1 over 9. Multiplied by negative 5, we will have this negative 5 over 9. Next, negative 1/3 times negative 11, we get positive 11 over 3, then the negative 3 follows. When we combine the first two fractions, we will get negative 6 over 9 and simplify to be negative 2 over 3. When we combine positive 11 over 3 minus 3, we will have this positive 2 over 3. The negative 2/3 plus positive 2/3, we will get 0. Thus, the p of negative 1/3 is 0. We are able to show that p of 3 is equal to p of negative 1 is equal to p of negative 1/3, all equal to 0. Now, let us verify the relationship between the zeros and the coefficients. We have here the three relationships. Let's begin with the first. Substituting the corresponding values, we have now this 3 plus negative 1 plus the negative 1/3. Is it equal to the negative of b over a? And that is negative 5 for b over a is positive 3. On the left side, we can show that the integers can be a fraction. The 3 becomes 9 over 3, the negative 1 becomes 3 over 3, and this we have this negative 1/3 again, equals, the right side is simplified into positive 5 over 3. Simplifying the left side, it is now equal to 5 over 3 equals the right side with the same value 5 over 3. Therefore, the first relationship is verified. Let's proceed with the second. Let us substitute the corresponding values. 3 times negative 1 plus negative 1 times negative of 1/3 plus negative 1/3 times 3. Is it equal to c over a? The c is negative 11 over the a, which is 3. This 3 times negative 1 is negative 3. Negative 1 times negative 1/3 is positive 1/3. Negative 1/3 times 3, negative 1, equals the negative 11 over 3. We can combine this negative 3 and negative 1. It becomes negative 4, and that is equivalent to the fraction negative 12 over 3. Then plus this 1/3 equals negative 11 over 3. Simplifying the left side, we will come to this negative 11 over 3. That is the same value on the right side. Then we are able to verify the second relationship. Let's go to the third relationship. Let us substitute the values. We have this 3 times negative 1 times negative 1/3. Is it equal to the negative of d over a? The values are negative of negative 3. That is the value of d over a, which is 3. On the left side, we can simplify this into positive 1. On the right side, we have the same value, which is positive 1. Then we're able to see that the third relationship is verified. Example 2. Verify that 4, negative 2, 1/2 are the zeros of the cubic polynomial p of x equals 2x cubed minus 5x squared minus 14x plus 8. And then verify the relationship between the zeros and the coefficients. Take note that in our polynomial, a is equal to 2, the coefficient of x cubed. B is equal to negative 5, the coefficient of x squared. C is the coefficient of x, that is negative 14. And D is the constant, positive 8. Now to verify that 4, negative 2, 1/2 are the zeros of the cubic polynomial, we need to check P of 4 is equal to P of negative 2 is equal to P of 1/2. All must be equal to 0. Now let's start with P of 4. Evaluating this, we have this 2 times 4 cubed minus 5 times 4 squared minus 14 times 4 plus 8. This 4 cubed is 64 times 2 becomes 128. Then 4 squared is 16 times negative 5. We have this negative 80 here. 14 times 4 is 56. We have this minus 56, then plus 8. When we simplify these numbers, the answer is 0. So P of 4 equals 0. What about P of negative 2? Evaluating now, we have this 2 times cube of negative 2 minus 5 times the square of negative 2 minus 14 times negative 2, then plus 8. The cube of negative 2 is negative 8 times 2 will be negative 16. The square of negative 2 is positive 4 times negative 5, we get this negative 20. Negative 14 times negative 2 is positive 28, then plus 8. When we simplify the numbers, we will get 0. So P of negative 2 is 0. Then we go to P of 1/2. When we evaluate, we will get 2 times the cube of 1/2 minus 5 times the square of 1/2 minus 14 times 1/2, then plus 8. We simplify 1/2 cube, we get 1 over 8, then times 2, we will get 1/4. Then the square of 1/2 is 1/4 times negative 5, we will get negative 5 over 4. Minus the 14 times 1/2 is 7. Then we copy plus 8. When we combine the fraction 1/4 minus 5 over 4, we will get negative 4 over 4. That is equivalent to negative 1. Then negative 7 is here. Then plus 8. All becomes 0. So P of 1/2 is 0. Thus, we are able to verify that the 4, negative 2, and 1/2 are the zeros of the polynomial. Let us proceed to verify the relationship between the zeros and the coefficients. Let's begin with the first relationship. We substitute the corresponding values. We have now 4 plus negative 2 plus 1/2 equals the negative b over a, and that is the negative of negative 5 over 2. We simplify, the left side becomes 4 and negative 2 here becomes positive 2 plus 1/2. Is it equal to positive 5 over 2? The sum 2 and 1/2 will give 5 over 2. That is equal to the right side. Therefore, we're able to verify the first relationship. Let's go to the second relationship. Let us substitute the values. We have 4 times negative 2 plus negative 2 times 1/2 plus 1/2 times 4 equals C over A. The C is negative 14 over A, which is 2. 4 times negative 2 is negative 8. Then negative 2 times 1/2 will give negative 1. 1/2 times 4 is positive 2 equals, we simplify this fraction as negative 7. When we simplify the left side, it will give us negative 7 that is equal to the right side. Therefore, we're able to verify the second relationship. What about the third relationship? Let us substitute the values. 4 times negative 2 times 1 half. Is it equal to the negative of d over a? Negative, the d is 8. We write it here, and a is 2. When we multiply, the left side becomes negative 4, which is equal to the right side that is simplified into negative 4. We're able to verify the third relationship. Hi everyone, today we're going to study division of polynomials. Here are the steps. Number 1, arrange the terms of the dividend and the divisor in decreasing order of their degrees. Step 2, to obtain the first term of the quotient, divide the highest degree term of the dividend by the highest degree term of the divisor. Then, carry out the division process. Step 3. Now, to obtain the second term of the quotient, divide the highest degree term of the new dividend by the highest degree term of the divisor. Again, carry out the division process. Step 4. Stop the process when the degree of remainder is less than the degree of the divisor. Let's have this division algorithm for polynomials. It says, if p of x and g of x are any two polynomials, with g of x not equal to 0, then we can find polynomials q of x and r of x, such that p of x equals g of x times q of x plus r of x, where r of x equals 0 or degree of r of x is less than degree of g of x. Example 1. Divide 3x cubed plus x squared plus 2x plus 5 by 1 plus 2x plus x squared. The first step is to arrange the terms of the dividend and the divisor in the decreasing order of their degrees. After that, we put them in the division box. So the dividend is here, 3x cubed plus x squared plus 2x plus 5. For the divisor, we have this x squared plus 2x plus 1. Let's begin our division process. This 3x cubed we will divide by x squared. The answer is 3x. We will put our answer above the 3x cubed. Next is, we multiply this 3x to each of the terms of our divisor. So 3x times x squared will be 3x cubed. 3x times 2x is 6x squared. 3x times positive 1 is 3x. Then we subtract. When we subtract, we know that we need to change the sign of the terms of the subtrahend, meaning this is positive now becomes negative. From positive becomes negative. From positive becomes negative. Then we add. This 3x cubed and negative 3x cubed will cancel each other. So positive x squared minus 6x squared, we have now this negative 5x squared. Positive 2x and minus 3x becomes negative x. Then we bring down the positive 5. This is now our new dividend. This negative 5x squared we now divide by x squared. The answer is negative 5. Then we write the answer in here. Next, we multiply negative 5 to each of the terms of our divisor. And the answer we will place down here. So negative 5 times x squared is negative 5x squared. Negative 5 times 2x is negative 10x. Negative 5 times 1 is negative 5. Then we subtract. We will change the signs of the terms of our subtrahend. This negative 5x squared becomes positive. The negative becomes positive. This negative 5 becomes positive. Then we add. This negative 5x squared and positive 5x squared will cancel out. Then this negative x plus the positive 10x is 9x. Positive 5 plus 5 is now plus 10. From here, we stopped because our new dividend here, 9x plus 10, has lesser degree than our divisor. So, the quotient is 3x minus 5 and the remainder is 9x plus 10. Example 2. Divide 3x squared minus x cubed minus 3x plus 5 by x minus 1 minus x squared and verify the division algorithm. First, we arrange the terms of the dividend and the divisor in the decreasing order of their degrees. After that, we put them in the division box. So it becomes like this. Our dividend now is negative x cubed plus 3x squared minus 3x plus 5. And the divisor, negative x squared plus x minus 1. Let's begin our division. The first term here, negative x cubed, is divided by the negative x squared. The answer is x, so we write the answer above the negative x cubed. Next, we multiply this x to each of the terms of the divisor. The answer is negative x cubed plus x squared minus x. Then we subtract. We change the sign of the terms of the subtrahend. This negative becomes positive. The positive becomes negative. Negative becomes positive. Then we add. Negative x cubed plus positive x cubed cancels out. Positive 3x squared minus x squared is 2x squared. Negative 3x plus x is negative 2x. Then we bring down plus 5. This is now our new dividend. So this 2x squared we divide by negative x squared. The answer is negative 2. Next, we multiply negative 2 to each of the terms of our divisor. So we have this 2x squared minus 2x plus 2. Then we subtract. Again, we change the sign of the terms of the subtrahend. This positive becomes negative, negative becomes positive, positive becomes negative. Then we add. The 2x squared plus negative 2x squared will cancel out. Negative 2x plus the positive 2x will cancel out also. Positive 5 minus 2, the answer is positive 3. This is the new dividend, but we stop here because the degree of the dividend or the new dividend is less than the degree of the divisor. Therefore, the quotient is this x minus 2 and the remainder is 3. Now we check or verify the division algorithm. That is, the dividend is equal to divisor times the quotient plus the remainder. When we substitute the corresponding values, we have this divisor x minus 1 minus x squared. The quotient is x minus 2 plus the remainder plus 3. When we simplify the product of divisor and quotient, we will have this polynomial x squared minus 2x minus x plus 2 minus x cubed plus 2x squared, then the remainder plus 3. Let us combine the like terms inside the grouping symbol. This x squared combined with 2x squared. So we have 3x squared. Negative 2x and then negative x becomes negative 3x. Then we have this plus 2. Then we have the negative x cubed. Again, we copy the remainder plus 3 in here. Let us now remove the grouping symbol here and combine the constant 2 with the remainder. We will have this 3x squared minus x cubed minus 3x plus 5. And this polynomial is equal to our dividend. Example 3. Find the zeros of x cubed minus 3x squared minus x plus 3 if one of its zeros is 1. Since 1 is a zero of the polynomial, then x minus 1 is a factor of x cubed minus 3x squared minus x plus 3. Thus, this cubic polynomial here can be divided by x minus 1. So, we write our dividend inside the division box, x minus 1 outside. This is our divisor. Let's begin the division. X cubed divided by x. The answer is x squared. X squared times x, we have x cubed. X squared times negative 1, we have negative x squared. Then we subtract. We change the sign of the terms of the subtrahend. This x cubed becomes negative. This negative becomes positive. Then we add. X cubed plus negative x cubed cancel out. Negative 3x squared plus x squared. We have this negative 2x squared. Then we bring down this negative x. This is our new dividend. We divide negative 2x squared by x. The answer is negative 2x. The negative 2x we multiply to each of the terms of our divisor. So we will have this negative 2x squared, then plus 2x. Then we subtract. We change the sign again of the terms of the subtrahend. The negative becomes positive, the positive becomes negative. Then we proceed to addition. The negative 2x squared plus 2x squared will cancel out. The negative x plus the negative 2x, we will get the negative 3x. Then we bring down the plus 3. Now we divide negative 3x by x. The answer is negative 3. Then we multiply negative 3 to each of the terms of the divisor. We write the answer down here. So we have negative 3x plus 3. Then we subtract. Again, we change the sign of the terms of the subtrahend. Then we add. Negative 3x plus 3x will cancel out. Positive 3 plus the negative 3 is 0. From here we stop because this is already 0. Or we say that the degree of the dividend is less than the degree of divisor. So the quotient is x squared minus 2x minus 3. And the remainder is 0. Actually, no need to mention the remainder if it is 0. By division algorithm, we can write this x cubed minus 3x squared minus x plus 3 equals x minus 1 times the quantity x squared minus 2x minus 3. Next is, let us factorize the trinomial here and the answer we will get and write here. So the dividend is equal to x minus 1 times the factors of x squared minus 2x minus 3, which are x minus 3 and x plus 1. We equate each factor to 0 and solve for x. So we have this x minus 1 equals 0, which is the given, x minus 3 equals 0 coming from here, and the x plus 1 equals 0. When we solve for the x, we have x equals 1, here x equals 3, Here, x equals -1. These are the zeros of our polynomial. Example 4. Find all zeros of 2x raised to 4 minus 3x cubed minus 3x squared plus 6x minus 2 if two of its zeros are square root of 2 and negative square root of 2. Since square root of 2 and negative square root of 2 are zeros of the polynomial, then we can write x minus square root of 2 times x plus square root of 2. When we multiply this, we will get x squared minus 2. This binomial here is a factor of the given polynomial. And that means we can divide this polynomial by x squared minus 2. So let us put them in division box. The dividend is inside. Our x squared minus 2 is the divisor. Let us proceed to division. 2x power 4 divided by x squared. 2x squared. Then we multiply 2x squared to each of the terms of the divisor. So we have this 2x power 4 and then negative 4x squared. We place the negative 4x squared below this negative 3x squared. Then we subtract. We will change the sign of the terms of the subtrahend. So this is now negative and this is now positive. The 2x power 4 plus negative 2x power 4 will cancel out. Then we combine this negative 3x squared plus the positive 4x squared. We will have x squared. Then we bring down the negative 3x cubed, also the 6x minus 2. This is now the new dividend. This negative 3x cubed divided by x squared. The answer is negative 3x. This negative 3x we multiply to each of the terms of the divisor. The answer is negative 3x cubed and positive 6x. Let us subtract. Let us change the sign of the terms of the subtrahend. This negative becomes positive. The positive becomes negative. Then we add negative 3x cubed plus 3x cubed, cancel. Positive 6x plus negative 6x also cancel out. Now we bring down x squared and the negative 2. We divide x squared by x squared. The answer is plus 1. This 1 we multiply to each of the terms of our divisor. The answer is x squared minus 2. When we subtract, the answer will be 0. From here we stop because the remainder is 0, or we say that the degree of remainder is less than degree of divisor. So by division algorithm, we can write the dividend is equal to the x squared minus 2, this is the divisor, times our quotient 2x squared minus 3x plus 1. The remainder, no need to write. The next step here, we need to factorize this trinomial, the 2x squared minus 3x plus 1. When we factorize, first we write it here. We're going to split the middle term into two terms in such a way that the product must be 2x squared. We got this value when we multiply this 2x squared by the constant 1. So we write it like this: 2x squared minus 2x minus x plus 1. The negative 3x is split into negative 2x and negative x. When we multiply negative 2x by negative x, the answer is positive 2x squared. Then we group the first two terms here and the last two terms. In the first two terms, there is a common factor, and that common is 2x. When we factor it out, what remains in the first group is x minus 1. In the second group, the common is the negative sign. When we pull it out, what remains in the second group is the x minus 1. On this line, we have now two big groups. and we can observe that there is a common binomial. We can put that common outside. So it becomes like this. The x minus 1, which is the common, is factored out. Then what remains here is the 2x, and in here, minus 1. So these are the factors of our trinomial here. Then we write again our division algorithm. The given polynomial or the dividend is now equal to like this. We show now this x minus square root of 2 and the x plus square root of 2 representing the x squared minus 2. Then we write this x minus 1, also the 2x minus 1. We equate each factor to 0 and solve for x. Therefore, we will have like this. This x equals square root of 2 coming from this. The x equals negative square root of 2 coming from this. Actually, these are the given here. Now, for x minus 1, it becomes x equals 1. The x equals 1/2 comes from 2x minus 1. These are the zeros of the polynomial.